morning.
Good morning.
Those of you who came here expecting to see someone from the United Kingdom, I disappoint you. I was born in Grenada, have lived in 6 Caribbean countries. Admittedly, I did spend 8.5% of my life studying and working in the UK, but I don't have a UK passport. The topic is on the screen: Caribbean natural hazards. There are 7 major Caribbean natural hazards. I will speak about the hazards, about their impact on structures, current information for design I would outline, and the regulatory systems throughout the Caribbean. And lastly, I will say something about climate change and how it may affect engineers. So this is the region we're talking about, the Caribbean, and the hazards. Now, the hazards are natural, and to call the hazards disasters is to blaspheme, because God doesn't do anything which is bad. The disasters are because engineers like ourselves, architects, planners, and decision makers misbehave. The hazard which we have annually between June and November is the hurricane hazard, and most particularly its characteristically high wind speeds. You will notice from the map of the Caribbean that Trinidad and Tobago are almost completely outside of the hurricane zone. As you go from north to south, hurricanes become less frequent. We speak more about that a bit later. This is called Hurricane Alley, and if you're fortunate enough to live in Antigua and Barbuda, then you have many experiences of hurricanes. Even in Trinidad and Tobago, we have many tropical storms, some of which become hurricanes. This is, in this diagram, you see the tracks of tropical storms over a period of 150 years, passing through a circle with a radius of 250 kilometers, focused on Port of Spain. Included among that set is the great hurricane which went through the south of Trinidad in 1933, of which an important calypso was composed. In addition to the fundamental wind speeds in a hurricane, we have in the Caribbean dramatic topographies which lead to an acceleration in some cases and a sheltering in other cases of the wind. Because of the importance of topography on wind speeds for structural design, in the mid-1980s, we conducted a wind tunnel test on the island of Nevis at the Boundary Layer Wind Tunnel Laboratory of the University of Western Ontario. So in the picture, you can see Nevis, the whole island of Nevis, on a turntable, which was turned around in 8 different directions to determine how topography affected wind speeds. In this following cartoon, it summarizes the findings. So with the wind offshore approaching the island, over relatively smooth ocean, you have the gradient wind. Gradient wind is the wind so high above the surface of the earth that is not affected by the surface of the earth. So the gradient wind is represented in this diagram by 100%. As a hurricane approaches land at a height of 10 meters above ground, you have 80% gradient wind. When it comes ashore on the windward side, because of the friction of the land, it drops to 60% of the gradient wind. It accelerates over ridges and mountains to 120% of the gradient wind, and sheltered leeward side it drops to 40%. So the wind forces, which are a square of the wind speed, can be 9 times as high at the peak as it is on the leeward side. Tremendous differences because of topography. Carrying out wind tunnel tests are quite expensive, but there is computational methods for determining the effect of topography and wind speeds. This is the island of Antigua, where that method was used and can be used on any of the islands. That's a fairly inexpensive process. In addition to winds, we have waves. Waves are generated by winds, but you also get major wave events in the Caribbean in the early part of the year before the hurricane season. And they cause a lot of damage on the west coasts of our islands and damage the beaches, which the tourists like to enjoy. And then we have storm surge. Storm surge is also generated by hurricanes. And storm surge is the bodily rising of the ocean as it's pushed forward towards the landmass by the hurricanes. Storm surge is not an issue to be concerned about in the small islands of the Eastern Caribbean. It's not a concern for Trinidad and Tobago. But it is a concern for the larger islands in the Greater Antilles, and more particularly in Belize. In Belize, in 1961, there was Hurricane Hattie, which destroyed much of Belize City. And because of that, in the 1990s, we carried out research on the storm surge hazard in Belize. And here we have the storm surge events of different return periods, 10 years, 25 years, 50 years, and 100 years. The reason for Belmopan, the new capital of Belize, being so far inland is because of the destruction of Belize City in 1961. However, much of the development after the building of Belmopan has not occurred in Belmopan, but back in Belize City. So the only referral hospital in the country of Belize was newly constructed in the mid-1990s in Belize City. And whenever a hurricane is approaching Belize, they have to evacuate the only referral hospital in Belize. That's how we behave. And then we have rainfall. Now rainfall accompanies hurricanes, but you also get major rain events without hurricanes. This particular rain event is very significant for Mahatma Gandhi and for me, because it occurred on the national holiday in India, 2nd of October. But this was the event in Barbados, and I was the only one who made it to work that day. Because I went to work before the flooding occurred. On that day, 500 millimeters of rain fell in 24 hours. And that was a great event of the 2nd of October 1970. So rain and flooding causes more losses cumulatively in the Caribbean than any of the other natural hazards. And because of that, the Caribbean Development Bank gave the Caribbean Regional Organization for Standards and Quality $200,000 a few years ago to employ consultants from a faraway place to work with a local governmental agency based in Barbados to carry out flood hazard mapping of several countries in the Caribbean, including Trinidad and Tobago and St. Vincent and the Grenadines. When the floods occurred in St. Vincent on Christmas Eve, immediately afterwards on Boxing Day, I wrote to CrossQ and to CDB and asked them whether the study which was done a few years before had been sent to St. Vincent for their information, and if so, which agency in St. Vincent was the recipient of the study. As of the 23rd of January 2014, I have had no answer from the CBB, who spent $200,000, and CrossQ, who executed the project, as to where the study was in St. Vincent. So we do studies to put them on shelves, not to use them. In the study, which is several volumes and takes up a DVD or two CD ROMs, there are flood hazard maps of Trinidad and Tobago. This particular map is of Port of Spain. I can't decipher it particularly well, and most of the files that were given to me at my request, I can't open them because they're in a format which I can't access. But there are copies of those files currently in 97 Fabric Road near the Oval in Trinidad. Let's move on to geological hazards. And the one that really excites us is earthquake hazard. But earthquake hazard is very interesting because it includes the Caribbean plate, which is moving towards the east, towards Africa. And many of you would have heard of Marcus Garvey and his Back to Africa movement of the 1930s. And you thought you didn't know what he was really talking about, is the movement of the Caribbean. That move towards Africa is taking place all the time at a speed of 20 millimeters per year. We'll get there sometime. It is not the most dramatic move of in the Caribbean because the Cocos Plate is moving at 60 millimeters per year, and the Nazca Plate here at about 40 millimeters per year. But nevertheless, that movement of the Caribbean Plate relative to the North American Plate is important. This is a seismic hazard map of the Caribbean with peak ground accelerations, and the different colors indicate different degrees of severity. Note in particular that Dominican Republic is red, Haiti is yellow, means not so serious. There's red here in Cuba, there's red in Jamaica. So in the middle of these three red blobs is the yellow blob of Haiti. So sometimes our seismic hazard maps are determined for sociological and political reasons. In the Eastern Caribbean, we have a very confused situation in the southeast, where Trinidad is, and in the northeast, where Antigua is. But in the middle part, the situation is easier to understand because there we have a subduction zone. I did not say a seduction zone. We may also have that. But this is a subduction zone. This is where the North American Plate is subducted or dips beneath the Caribbean Plate. And the Caribbean Plate is moving towards the east, and the North American Plate relatively moving towards the west. And displaced from the junction of the two plates is where the volcanic activity occurs, approximately 150 kilometers west of the junction. Where the junction occurs, immediately above that is the island of Barbados. So that's why Barbadians feel that they're safe from earthquakes, because they're immediately above the junction. I have news for them. In the Eastern Caribbean, we've had many important earthquakes throughout post-Columbian history. The largest of them recorded was in 1843, which caused deaths of thousands of people in Guadeloupe. And the last damaging one in Barbados was the 1953 earthquake. Barbados is south of here. 1953 earthquake, which destroyed the Combermere School in Barbados, the oldest secondary school in Barbados. Most Barbadians do not remember that event. Most Barbadians weren't alive in 1953. Going back to Hispaniola, back to Haiti. There's Haiti again, in yellow, which means not much of a problem. However, the world knew that Haiti is located in an earthquake-prone area. I went to Haiti after the earthquake, which occurred 4 years and 11 days ago, and spoke to architects and engineer friends of mine there, and they all said to me, we never designed for earthquakes. Earthquakes occur in the Dominican Republic, not in Haiti. So, in the 20th century, they were right. There was a remarkable sequence of earthquakes in the Dominican Republic over an 8-year period, from 1946 to 1953, 8 years. These 5 earthquakes occurred in the Dominican Republic. The smallest of those 5 earthquakes, all of which occurred in an 8-year period, the smallest of them was the same size as the earthquake which killed 230,000 people in Haiti in January 2010, magnitude 7. And the largest of those earthquakes was the largest earthquake instrumentally measured anywhere in the Caribbean. It was about 8.1 magnitude. But earthquakes don't occur in Haiti. In Haiti they speak Creole, in the Dominican Republic they speak Spanish, so they can't have the same seismic activity in both places. And then we have tsunamis. But before we have tsunamis, we have volcanic activity. The subduction zone generates not only big earthquakes, but also volcanic activity. And volcanic activity affects not only the volcanic islands, it also affects other islands. So, Barbados has topsoil on top of the coral rock. And all the topsoil of Barbados comes from volcanic eruptions in St. Vincent. St. Vincent is west of Barbados. The trade winds blow from east to west. So how does the ash get from St. Vincent to Barbados? It gets there because when you have a violent eruption of La Soufrière in St. Vincent, the eruption goes up into the anti-trade layer above 10,000 meters. And at that layer, the winds blow from west to east and dumps the ash in Barbados. The most recent event being Good Friday, 1979, where the entire island of Barbados was covered with ash from the Soufrière eruption. The tsunamis have killed many people in the Caribbean. In fact, prior to the great event in Japan, the Fukushima event in Japan recently, more people were killed by tsunamis in the Caribbean in the past 170 years than were killed in the entire Pacific Ocean. But we don't remember those events. The most recent major loss of life from tsunamis in the Caribbean was in 1946, when 1,800 people died in Hispaniola. The tsunami that we are keeping an eye on, the tsunami generating location that we're keeping an eye on is Kikamjeni, which is a submarine volcano just north of Grenada. That's Kikamjeni here. And that has been studied by former Professor John Shepherd of Seismic Research Center of the University of the West Indies. And they determined the likely tsunami heights in different parts of the Eastern Caribbean are quite low in Trinidad and Tobago. And in any case, you have about an hour, half an hour to get out of the way, 30 minutes for Tobago, and more than that, nearly an hour before the tsunami strikes the north coast of Trinidad. So you don't have to worry too much about that. Let's see how these events have impacted on structures in the Caribbean in recent times. As you look at the pictures which follow, you realize that any material can be used sufficiently badly that the resulting structure is vulnerable. So we have unreinforced modern masonry, which can be destroyed not only by earthquakes, but in this case, by hurricanes, hurricane winds. And then you have monumental structures from the distant past, which have survived for over 100 years. So people say, if it lasted that long, it must be strong enough, but that's not the case. Winds can destroy massive masonry structures. They can also destroy the timber roofs of cathedrals, and it can also destroy timber schools. Steel structures could be stronger, but they're not necessarily so, and they can be destroyed by the winds, and even reinforced concrete can be sufficiently badly designed, detailed, and constructed that they can be destroyed, in this case, by a hurricane. There are several reinforced concrete structures which were destroyed by Hurricane David in Dominica in 1979. When we have hurricanes, we lose our public utilities. Our transmission and distribution systems are disrupted. The wood pole systems which come out of the USA are not designed for Caribbean hurricanes. And many of our steel towers are also sufficiently badly engineered that they too collapse in hurricanes. We are located, this conference, in Trinity, Arabia, and therefore we have to be concerned about the oil industry. So the largest oil refinery in the world in 1989 was in St. Croix. 800,000 barrels a day was the product of that oil refinery, which was then owned by Hess. And in that oil refinery in St. Croix, Hurricane Hugo destroyed all of the oil storage tanks. And of course, it was tremendous pollution as the oil was sucked out of the tanks. And then that's not how you want your hospital to look after an event like a hurricane, because you need the hospital to see after the injured. But too often our hospitals fail us. And this picture should have some resonance in Trinidad and Tobago, because it was designed, constructed, and funded by Trinidadians and Tobagonians. I mustn't leave Tobago out of it. And a famous Tobagonian went to Grenada in January after Hurricane Ivan and said to the Prime Minister, Dr. Keith Mitchell, said, Dr. Mitchell, you will have an inquiry, won't you? And Dr. Keith Mitchell said to the famous Tobagonian, you can't treat your friends like that. Mr. Raymond? You can't treat your friends like that. No inquiry. There was a very fortunate event in 2003 in the Dominican Republic. There was an earthquake, magnitude 6.4, and it occurred at a wonderful time, 45 minutes after midnight. Several important buildings collapsed. No one was killed because of the time of the event. So that bank lost its top story. This fabrication shop lost its roof. This shopping center collapsed, and there were no one present in any of those buildings. And even more dramatically, that 3-story school became a 1.5-story school. This is the bottom story of the school. That's the middle story of the school. And inevitably, everyone there would have been crushed to an unrecognizable state, and everyone in this middle story would also have died. But it occurred at a time when the school was completely empty, so no one died. It was 2003 in Dominican Republic. In 1997, very close to Trinidad and Tobago, on the Caribbean coast, of the northeast coast of Venezuela, there was an earthquake on the 9th of July, 1997, and 4 to 6 children died at that school. And 56 children died in this school. And in that school, the second school, there was another block which was 3 stories there. This became 2 stories. And the 2 upper stories were held up by chairs and tables. The chairs and tables supported the upper 2 stories. That was quite remarkable. The Japanese have this as a drill in their schools. Let's go back to the oil industry, at which you're very concerned. In 1974, there was an earthquake in Antigua, which destroyed the company. The West Indian Oil Company never recovered from that earthquake. All of its tanks failed, and if all of the tanks fail at the same time, the berm surrounding the tank farm is usually not high enough to contain the spill. So the spill overtopped the berm and headed towards the white sand beaches of Antigua. Coming closer to our present generation, we have the Haitian earthquake, of which there are many images which can fill up 6 hours of your time. I won't do that. But here is the palace. Here is the presidential palace, before and after. The presidential palace was not built by third world engineers and architects. It was built by the United States military during the period when, between 1917 and 1934, when the US occupied Haiti, so as to get the loans to JP Morgan and other US banks repaid. During that earthquake, Haiti also lost its cathedral, which is a reinforced concrete structure. God only helps those who help themselves. And Haiti has many examples of bad design and construction. This was a good indication that you must have strong columns. Your columns must be stronger than your beams. Columns must not fail. When columns fail, people get killed. And there again, this is a 5-story building. You can only see 3 stories, or that's the first story, and that's the second story. And if you look closely, maybe I can help you look a bit closely. You can see how little stirrups there are. In fact, a complete absence of stirrups in this column. So Haiti was a good example of very bad design, very bad detailing, and very bad construction. And in Haiti, they used, in some cases, flat plate construction, and flat plate construction kills people in earthquakes. Something which the industry doesn't like to think too much about is liquefaction. But liquefaction is a fact of life in many, a potential fact of life in many of our coastal projects. In Antigua in 1994, there was liquefaction at the port. And in Haiti, in 2010, there was dramatic liquefaction at several port facilities. This before picture, you see, is dark, and the white indicates sand being pumped up from underneath because of liquefaction. Liquefaction also occurred in the Cariaco earthquake, where you saw the schools which were damaged. There was severe liquefaction in Cariaco in 1997. So many of our new port facilities, which include pumped, dredged fill to create new land, are time bombs, really. There are disasters waiting to happen. So that's what liquefaction looks like at a port facility. And this is, if you want to create a white sand beach, then ask for an earthquake. Because there you can see no beach, and there you can see that lovely beach. Of course, you have lost the jetty. But never mind, you can rebuild the jetty, but you have your beach. That's liquefaction. Back to the oil industry. Damage to damage to tanks. You saw the damage to tanks from hurricanes in St. Croix, and damage to tanks in Antigua from earthquakes, and this damage to these tanks in Haiti. And the form of damage, there was what is known as the elephant's foot buckling of the shell of the tank. There was a study done in Puerto Rico about 10 years ago of water and oil storage tanks, and they determined that 90% of the tanks in Puerto Rico were vulnerable to either wind or earthquake or both. Now, we do have information for design. We can't say we don't know what to do, because we have a lot of information about what we should be doing. Dr. Myron Chin was the chairman of the Caribbean Uniform Building Code project in the 1980s, which lasted from 1980 to 1985. And it includes 13 volumes, of which 9 are illustrated there. But who uses them is the question. In cubic, there was information on wind. That's the cubic map for wind. We've updated it recently in this 2008 project. There was information on the earthquake hazard. Those are the cubic cubic values for Z values, and they're compared with what was then used for UBC and CR. The information is available, but is it used? If you go back to the Haiti earthquake, the Haiti earthquake is exhibited by this red line. That's the spectrum of the Haiti earthquake. It falls below the 1980 standard for the Dominican Republic, that which is the yellow line, and falls way below the green line, which is the new Dominican Republic code. Dominican Republic shares an island with Haiti. There's no reason to treat one side of the border differently from the other. As far as wind is concerned, we have new wind hazard maps for the whole Caribbean basin. This is the 50-year wind speeds for the Caribbean. And I should explain something. Mr. Riley talked about the use of IBC 2009, which references ASC 7 2005. In ASC 2005, the basic wind speed is a 50-year return period. But that, in fact, that 50-year return period was not determined directly. What they did in the USA is to take the 700-year return period and adopt a load factor of 1.6. They then divided the 700-year wind speed by the square root of 1.6 to determine what the 50-year return period would be. So the 50-year return period was, in fact, the 700-year return period divided by the square root of 1.6. Now, that poses a problem for all of the Caribbean. In this series of diagrams, you see is illustrated the problem. In 1971, we discovered, thanks to Norris Helliwell of the UK Meteorological Office, that we should not be using these straight lines, which were in our 1970 CCEO code, to relate wind speeds of one return period to wind speeds of another return period. We should be using the curved lines, which we did do in 1981 edition. And then in 1997, Chris Geerts of the Netherlands came up with this relationship of wind speeds of different return periods without knowing what Helliwell had done. And then in 2008, Peter Vickery came up with this diagram without knowing what Chris Geerts had done in 97 or Helliwell in 1971. And what they're all saying is that as you approach the equator in the North Atlantic, the ratio of very rare wind speeds to very frequent wind speeds increases. The ratio of the rare wind speed to the frequent wind speed, that ratio, that increases. And that means that we have to pay attention when we use foreign standards. And so what it means is that we should not be using ASCE 705 and plug into it our 50-year return period wind speed in the Caribbean. Because if we do that, we have to use a variable load factor. The load factor is defined as a ratio of the V700 to the V50 all squared. That's what the load factor is. That's the definition of the load factor in ASCE 7. And the definition of the importance factor in ASCE 705 is the V1700 over V700 all squared. So we have to have the 700-year wind speed for the Caribbean, which we do, and the 1700-year wind speed for the Caribbean, which we do. The reason for the large islands being shaded over is that with the large islands we have another factor to consider, which is the diminution of the strength of the hurricane as it passes over a large landmass. So those four largest islands in the Caribbean have unique maps of all for themselves. This is the one for Jamaica for the 700-year return period. For the small islands, we have a table, and the table is there. And this is, in fact, increase the size of Trinidad and Tobago. There we are, Trinidad South and Trinidad North. And we go across to 700 and 1700. So we have the information. Since 2008. So the recommended procedure, if using ASCE 705, is to use the 700-year wind speed with a load factor of 1 for Category 2 buildings, and 1700-year wind speed load factor of 1, of an importance factor of 1 for Category 3 and 4 buildings. And that's very convenient, because most engineers know how to multiply by 1. And we've changed the load combinations in ASCE 705, and all of this information was presented in a paper which is on the internet since 2008. It was presented at a conference in Puerto Rico in 2009 by that UK specialist Tony Gibbs, and is now incorporated in ASCE 710. ASCE 710 no longer uses a 50-year return period, uses a 700 and 1700. And if you look at the appendices of ASCE 710, you certainly won't see any reference to my Puerto Rico paper. Let's talk about earthquakes. Between 2009 and 2011, the Seismic Research Center collaborated with the U Center out of Italy, funded by the municipality of Milan, to produce state-of-the-art seismic hazard assessment of the Eastern Caribbean. These islands were our area of responsibility. The project was co-coordinated by Professor Michele Calvi, who last week retired or resigned from his president of U Center, and by myself. Michele Calvi, as some of you would know, was recently convicted of manslaughter because he did not predict the L'Aquila earthquake of 2009, which killed over 200 people. But in order to deal with these islands, we had to study a much wider area. So that was the area being studied. And that information is currently available on the SRC website. That's the peak ground acceleration with the 475-year return period. We have to do this because this is consistent with people who still want to use cubic or some other codes. And this is the information for Trinidad and Tobago. And those are the numbers for Trinidad and Tobago. As you go south, you get it is less intense, the earthquake. If you're using the more modern standards, you need to have spectral accelerations at 0.2 second and 1 second. We have them for the Eastern Caribbean, and we have them for Trinidad and Tobago. So that's the 0.2 second numbers, and that's the 1 second numbers. And if you prefer to use graphs, then there are the graphs there. So we have the information, we don't have excuses. We just don't wish to use information. Now the regulatory systems in the Caribbean are very varied. The first thing you have to know is that all countries in the Commonwealth Caribbean, with the exceptions of Guyana and Trinidad and Tobago, have formal, printed, published building codes. It's only Guyana and Trinidad and Tobago that do not have formal, printed, comprehensive building codes. But when it comes to the laws, fewer than all have laws, and even fewer have enforcement. And you have the peculiarity in Barbados, where there is a formal published government document from 1993, Barbados National Building Code, but if you're doing work for the government of Barbados, you don't have to use it. So you have Barbados with a code, but no laws and no enforcement, and Trinidad with laws and enforcement, but no code. Now when it comes to enforcement, the enforcement in the Commonwealth Caribbean leaves much to be desired. In most places it's not effective. It is effective in some parts of the Caribbean, as illustrated by Hurricane Luis in 1995 in St. Martin. St. Martin is a small island divided into two, half Dutch, half French. One event impacted the whole of the small island. On the Dutch side, they lost 200% of the gross domestic product. On the French side, not much damage. What was the difference? The difference is enforcement. The French islands have the only effective enforcement system in the Caribbean. It's in Martinique and Guadeloupe and Cayenne. That's it. And there was a very famous engineer who died too young. His name was Peter Rice. He was involved in the Sydney Opera House and other great projects. But Peter Rice wrote a book called The Engineer Imagines. And in that book, he talks about the effectiveness of the enforcement system in France, where he did some work. And he says that others not so closely involved must also be asked to review the project, to question the assumptions and demand explanations. The presence of a competent, dedicated and skeptical check-in authority is also very important in this respect. And that's what you experience in Martinique and Guadeloupe and nowhere else in the Caribbean. In Martinique and Guadeloupe, the best engineers work in the check-in authorities. They're better than the designers. In Trinidad and Tobago, in fact in South Trinidad, there is the Atlantic LNG Train 4 Jetty 2, which had 4 layers of checking. That's how important they regarded checking. So CEP Limited did the structural engineering for Presticon, and the 4 layers of checking. The first one was internal at CEP. The second one was by Bechtel, who were the project managers. And they checked everything. There was strict adherence to the standards agreed in the contract. And if you wanted to vary from those standards, if you wanted to change a semicolon to a colon, then you had to get an expert opinion. So approval of variations through expert opinions was demanded by Bechtel. The specifications for calculations were checked, and they approved the software and the hardware being used for analysis. In addition to that, Bechtel had an outside firm of independent engineers to do a third check. In addition to that, the insurance company had their own engineers to do the 4th check. Checking is important because most engineers are human beings, in which case they make errors. Climate change. I'm nearly near the end of my talk, so let's talk about climate change. First of all, there's only one hurricane ever recorded in the South Atlantic. It was in 2004, went into the north of Brazil. There may have been other hurricanes in the South Atlantic in the pre-satellite era, we don't know. But the only hurricane ever recorded in the South Atlantic occurred in 2004. In the same year, 2004, there was Hurricane Ivan. There you see Hurricane Ivan between Tobago and Grenada. And on the website of the National Hurricane Center in Miami at that time, there was a statement that the most intense hurricane ever recorded so close to the equator in the North Atlantic was Hurricane Ivan as it approached Grenada. In 2008, there was an event in the west of Cuba, which hardly anybody knows about. Everyone knows about Tacloban in the Philippines. No one knows about Gustav in Cuba in 2008. But there you see the anemometer. It broke as it rose. It broke on a rising leg. And when it broke, it was recording 340 kilometers per hour. That is a world record for a tropical cyclone. So, are you convinced that we have climate change? If you're not convinced, I'll go a bit further. You know, I used to sleep with a blanket in Barbados in February and January, maybe as recently as 10 years ago. And then I took off the blanket and just had a sheet. I took off the sheet and just had my pajamas. And now you can imagine what I am wearing. Because the winter months in Barbados have become distinctly warmer. Not convinced? Okay. Proof positive. So, with global warming, we have rising sea levels, and we have the collapse of the Atlantic thermohaline circulation. You know, no prizes for anyone who wishes to define thermohaline circulation. But thermohaline circulation refers to a part of the larger scale ocean circulation that is driven by global density gradients created by surface heat and freshwater fluxes. So this is collapsing in the Atlantic, leading to climate change. So we have rising sea levels. Fortunately, in Barbados, the land is also rising because of the subduction zone effects. But the land is rising at half the speed of the ocean. So our relative sea level rise in Barbados is 50%, approximately 50% of the absolute sea level rise. And then we have greater storm surge during hurricanes. Now, we did a study funded by the World Bank in 2008, Georgia Tech, Applied Research Associates, and Tony Gibbs, about the effects of climate change on wind speeds for structural design in St. Lucia as a proxy for the Eastern Caribbean, which includes Tobago and Trinidad. And what we have in the North Atlantic are multi-decadal cycles. These cycles last between 20 and 30 years. And what we are at present in an upswing. This cycle is not ended. This upswing cycle is likely to end around 2025. That's the anticipation. So the projections for the average number of North Atlantic tropical cyclones in 2025 was made. And if you read the red at the bottom there, it indicates that when you combine the peak of the multi-decadal cycle, which has been going on for many, many centuries or millennia, with global warming, which in the North Atlantic could be as much as ½ degree Celsius by 2025, you get heightened hurricane activity. Whatever buildings we design today must take that into account. And what it indicates is that for category 2 building, by category of building I mean the ASCE category, not hurricane category, but building category. In other words, ordinary buildings like this, you have to increase wind speeds by about 13%. And for category 3 and 4 buildings like hospitals, you have to increase the wind speeds by about 10%. But those wind speeds are already higher anyway, with another 10% added onto those. So, that's what we should be doing today. So what should we do tomorrow? And my suggestion is that we do this tomorrow. That's all I have to say.